Okay, so the question being, how well, given just those raw values, can you estimate the natural frequency? And so once you get into the lab, you can go in there and actually measure the mass of the structure. You can even try to measure the stiffness, displace, measure force and displacement, and get an estimate of your stiffnesses directly, and get a little bit better estimate of omega n, and then try to assess how accurate the value is. But another comparison that you can make is by actually measuring, right, the response. Give it an initial condition and let it oscillate. But keep in mind that you can't directly measure the natural period, which would give you the natural frequency, undamped, right? Because you always have some damping, and even though you're going to see that one of the things I didn't do well on this design was put enough damping in there, it's a pretty lightly damped system, so you're going to find that the zeta is small, but it's not zero, and it'll allow you to see, when can I assume that my zeta is small enough so that, hey, my damped period is which I can measure, right? Because it's always damped. It's actually pretty close to my natural period, and the thing to recognize here is you can measure this guy, right, from your signal, because that's in reality what you have. You're trying to find the natural frequency, so you have to measure damping, and that's what we're going to talk about shortly. How do I measure this zeta value? I'm going to show you a method for doing that. So you can only estimate omega n if you have an estimate of zeta, which can be done by using the log decrement method. So you can see kind of the combination of methods that you have to use in order to finalize your estimates for these parameters. See, once you get an estimate for omega n, then you can compare it to your theoretical value, and you can see whether you're, how close you came to estimating, what you can actually observe in your system, because your stiffness might be different from what you expect, right? Or it might behave differently. And let's look at some reasons, actually. Before we look at the log decrement method, I want to show you at least a couple of reasons why your K and M values could be off. And let's look at the influence of the spring mass on undamped natural frequency, right? Normally, when we model these systems, we're making an assumption that, okay, we have this, sort of call it the main mass, and here's some bunch of little examples in this table from this book by Den Hartog that's referenced here at the end of these slides. But Den Hartog shows several simple systems and formulas for estimating the natural frequency a little bit better than if you were just to assume that, hey, I've got an ideal spring here. Remember, an ideal spring is a spring that you assume that there's no mass, but let's say that this spring here had some mass, little m here. The main mass is m, and this is a translational vibrating system. This relation here shows that when I estimate the natural frequency, I take that stiffness, take the main mass, but to the main mass I add about a third of that spring mass, right? Again, what we're doing is taking into account the fact that that mass in that spring is going to make itself known in the way the system actually vibrates. And so that's basically what is being done in each of these formulas, right? Even for this rotational system, you've got the rotational, actually this is this is mass, this is rotational inertia, right? And then there's a stiffness in that rotational or torsional shaft. And then here's the main rotational inertia. So very similar to actually the translational case. And then here's some other cases. The one that we've actually, because we've studied the cantilevered beam with a mass at the end, so look at this one, we would try to find if adding 0.23 times the beam mass would give us a better estimate of natural frequency than if we were to just ignore this mass. Right? Now these values that Den Hartog shows here, they're not experimentally determined, they're actually theoretically determined using a method which is kind of like an energy method called Rady's method, and it's described in this handout, this is actually a chapter from Thompson's book, for any of you that are interested. So again, given the mass of the actual element, you could add that, and that might give you a better estimate of your natural frequency. That's one possible source for why, when you go in estimate your natural frequency, assuming ideal stiffness, ideal mass. You go into the lab, eventually get out an estimated natural frequency. If there's a difference, one reason might be, that you didn't account for mass in the spring. The other reason might be that the stiffness might be off. So one way that you could approach this, let's say before you walk into lab, so that you feel a little bit more informed, is to maybe put some bounds on your undamped natural frequency estimate. In other words, don't focus so much on one value, because there's always going to be some uncertainty, right? So the influence of the spring mass suggests, maybe what you want to do is look at the range that you should expect. And here's just one example. Say you consider the case where the spring is massless, right? Which is the way we normally approach it. Then we can get one estimate of natural frequency. The alternative is to say that whatever spring I have, I'm going to take its full mass, add that to the main mass, and now I'm going to get another estimate of natural frequency. Right? This natural frequency is going to be lower than this one. So when I think of the bounds, actually, this one is much lower than this one, and so that natural frequency is less than that one, and in between is the actual, right? So I hope that my natural frequency, this tells you, at least walking into the lab, what range of frequencies you have. Think about how useful that can be. You already then know, what is the frequency content of your signals? How fast should I sample so I can collect signal? All of that information that's typically useful when you're going to go and make measurements comes out of making some simple estimates like this. Of course, we aren't just uncertain about what the mass might be. There might also be some uncertainty in the stiffness, right? So you could actually do a whole uncertainty analysis on this basic relation and find more accurate bounds on your natural frequency given whatever uncertainty you think you might have in the stiffness and the mass. I'm just trying to show you one way to estimate those bounds. Okay, so I think instead of doing an uncertainty analysis, you might think, hey, if I can estimate one really well, I'll get my bounds based on the one that I don't. And that's just the example I'm showing here. Think about which one of these, is it stiffness or mass, that you think you're less certain about on this one case, and then create some bounds and see how well that your actual one comes between those bounds. Good practice calculation, I think.